So welcome everyone to our new ideas seminar. For those of you who are not familiar with ideas, it's Carnegie Mellon's newest center for informed democracy and social cybersecurity. The area is focused on a lot of issues involving things to deal with digital trace data and how we can use them to better society. In particular, we're interested in issues such as disinformation, hate speech, insider threat, and of course, our today's topic, contact tracing. Today, I'm excited to introduce you to Po-Shen, who is a faculty member here at Carnegie Mellon, who is like this wizard inventor, as well as someone who just loves mathematics. And what he does is he's actually founded XP, which is a really kind of neat, innovative learning platform for people to let you choose how you want to learn. He's also been the coach for the, I'm going to get it wrong, but it's the Mathematical Olympiad team. He's been doing that since 2014. And of course, he teaches lots of cool things here at Carnegie Mellon as well. With that being said, I don't want to steal his thunder about the contact tracing stuff he's going to talk about now, and I will turn it over to Po. Po-Shen, take it away.
Wow, well, thank you. It's a real pleasure to be able to talk to you, talk to your community, and talk to everyone here. Good afternoon to you all, if it happens to be afternoon. Good morning if it's morning, or maybe it's in the middle of the night. I guess that's the beauty of being able to have any kind of talk over Zoom these days. But I'm a mathematician, and so normally what I think about is pure mathematics, and in particular within pure mathematics, I spend most of my time thinking about network theory. But today I'm going to be talking about contact tracing because I got involved in COVID-19 control after the outbreak, in some sense, paralyzed a lot of our society. And it came to me, I got a realization that you could try to use the network theory that we think about normally in math to come up with something that could help with controlling the spread of COVID. And today I'm actually going to talk about something which is very different from what most people do when they do digital contact tracing. And so actually, I do a lot of things differently. One of the things I do differently is the way I share my screen, is that I just put my screen behind me like this. So if you want to zoom in, if you zoom in on this video, if you, I guess, right click and pin this video, then you'll be able to see it more clearly. As you can see, my very advanced way of sharing the screen also apparently sometimes flips things around. But this is actually on purpose. That's because I'm talking today about flipping this perspective on contact tracing. And I want to discuss how we normally think about contact tracing and how, if you flip the perspective, actually possibly from a social science perspective, you could have significantly more impact in terms of controlling the spread of a disease. For that, let's first flip back and talk about the usual paradigm. So this is the way that people usually try to control a disease. In fact, human beings have used this method for the last 3,000 years. Whenever you had anybody who was sick, you would just throw them and all the people around them out of town, and that would help to protect everybody else. Fortunately, we're a little bit more humane now, and we don't cast everybody out of town. But if I want to talk through all of these things really quickly, yes, first test to go and find the positive cases, then trace to go and find out who has spent time with those people, and then you isolate the people who spent the time with the positive tests. And we, fortunately, these days support the ones that we're isolating, because otherwise, if you think about this from a behavioral science perspective, it's very hard to convince people to buy in. Now, unfortunately, this is too slow on its own to try to control COVID-19, primarily because in COVID-19, the disease spreads before you have symptoms, 48 hours before you have symptoms. And furthermore, it's fairly infectious. And so we happen to know now that unfortunately, in many parts of the world, COVID-19 is growing out of control. Because of this, people started thinking about ways to use smartphones or digital technologies in order to enhance the speed at which you could do this contact tracing. And the first thing that you try to do with a digital technology is to do exactly the old paradigm, but faster. And so that began an entire swarm of Bluetooth-based contact tracing apps or GPS-based contact tracing apps, where the contact tracing apps would do this. For every positive case, they would go and find out who was around those cases instantly and tell those people that they should go and quarantine. Now, if you looked at the the public discussion around these contact tracing apps, the standard ones, the ones that you all hear about, the standard discussion about them. At the beginning, people were optimistic. Then after a while, people were pessimistic. And then most recently, people have started to become optimistic again. In fact, there was even a paper published by some researchers, primarily from Google, also from Oxford, where the researchers were modeling what could be the impact of this particular entire class of contact tracing apps, this particular entire class of apps, which after you've been exposed to COVID would ask you to please quarantine. And inside this article, the researchers came up to the conclusion that actually, even with a low adoption rate, that those apps could actually have an impact. And I went and pulled out the headline that came out of the MIT Technology Review based on this particular preprint. This was a preprint that I just pointed to. And it said a new study from Oxford University and Google says that contact tracing apps reduce infections, hospitalizations, and deaths at almost any level of adoption. But now, if you go in a little bit deeper and look at what this is based on, because of course, if there's a model, the model has certain assumptions. I want to mention these assumptions because my understanding is that a lot of the audience here thinks about social science, possibly from a quantitative perspective, not just possibly, probably from a quantitative perspective. Maybe there are behavioral scientists here. And whenever you have a model, the model has assumptions. And if you look at the assumptions underneath, it makes an assumption, which is that when an app tells people, so the notified contacts, notified means that you have been exposed to COVID-19, the assumption is that 90% of them, so it's 90% likely to begin a quarantine until 14 days from initial exposure, with a 2% dropout rate each day for non-compliance. So the basic assumption that all of this was, that particular article was based on, was that if it's true that when you receive a notification that there was somebody who was positive that you were directly exposed to, then you'd have a 90% chance of complying with this voluntary quarantine. So this is an interesting assumption. I think actually for your community in particular, you might be quite interested in whether this assumption is realistic, that if you receive a non-enforceable notice that you have been exposed within 6 feet for at least 15 minutes to the COVID-19, and nobody knew who you were, would you be 90% likely to comply? I will say the particular 90% parameter is a parameter that's built into the modeling software that they were using. And the modeling software that they were using had also been used for studying manual contact tracing. In the manual contact tracing setting, actually 90% is quite realistic, because if somebody has gone to you and found out that you were a contact, and if this person might have been, say, from the government, and said, now, please quarantine for 14 days. If the government asked you to, they're fairly powerful. So if the government wanted to make sure that people are quarantining, it would. But the question becomes, if you're going to use a digital solution, what is a realistic percentage? Also, it's important to note, we have found out in most Western countries that people are not willing to install a digital solution unless it protects privacy. And so we expect that any digital solution has some anonymity inside it, so that there will be no way to actually force you to do anything. This is where the behavioral science or social science perspective become quite interesting, because then the question becomes, how do you actually incentivize people to do things? But let me dig a little bit deeper into this piece as well. So it actually turns out that if you think about it carefully, if you have been within 6 feet of somebody who's positive for at least 15 minutes, the chance that you are infected, just based only on that information of within 6 feet for 15 minutes, it turns out that that chance could be below 10%. And this is actually a very important detail that we actually should know. I should first of all also say, I'm not a biologist, I'm not a virologist. My number there is only based on doing some back of the envelope mathematical calculations, but I believe actually it's a very important question to ask, especially among the research community. If somebody is told by an app that they were within somebody else within the 6 feet for at least 15 minutes, what is the chance that you actually get sick? And what I put here is, if you want the back of the envelope analysis, well, the expected number of people that a positive person infects is, roughly speaking, the number of people that they directly contact within 6 feet for at least 15 minutes, times the probability that each of them gets infected. Why did I put this up here? It's because there's a notion of R0. And R0 is a number which is, roughly speaking, measuring the expected number of people an infected person infects. And if you remember the estimates on R0 back, say, in March, before people were wearing masks, before people were really social distancing, R0 might have been around 3. And if the typical person would infect about 3 people, you just think during the period of time that they were infectious, maybe their peak 3 days of infectiousness, how many people were they around within 6 feet for at least 15 minutes? Possibly quite a few. And if you use this formula to try to figure out what P is, you just divide the 3, which is this side, by the N, which is how many people they were around, and you'd come out to a number that is quite low. And no matter how you cut it, that number is going to be less than half. And at that point, then the question becomes a question of human behavior. If you're asked by somebody, not if you're asked, if you somehow were informed that you might be contagious, that you might have been infected, but if the likelihood that you're actually infected is well below half, and if it's not enforceable, what fraction of people will actually comply? This is a deep question, and I don't know the answer. But then what we decided to do is we decided to think about whether or not there might be a completely different way to try to attack the problem of pandemic spread. Because, as you can see, the manual way works. If you have somebody who actually finds somebody, if you find the contacts and you enforceably ask them to please quarantine, that will indeed suppress the spread of a disease. But the question becomes, what should you do with digital tools? If it has to be anonymous and non-enforceable, then suddenly there's the question of how the average human being will behave, because maybe they would actually require a much higher guarantee of being positive before they're willing to comply. Who knows? But we came up with a different idea completely. The completely different idea was, and this, by the way, is totally different from every other app-based method that has been deployed. And the method that we came up with was, what if instead of following the traditional paradigm, where you find the positive case and then you notify the people who have been directly near them to please isolate, what if we change that paradigm? I'm going to flip forward. What if we instead try to use the entire structure of the network? Because what we've just shown, I was just showing some little one positive person and the people that they were directly around. In that sort of a system, yes, you would be asking people to quarantine because those people have already been exposed. Makes sense. But what if you could I don't know how to pronounce this, pseudonymously? It's anonymously, but with pseudonyms. I'm using this word carefully because this is a computer science context where you guys might differentiate between the two meanings. But what if you collect an entire network without identifying each person individually with their personal information? But if you had this whole network, could you do something much more powerful? Maybe you don't need to just, for the positive case, inform the people around. And we came up with this idea. We flipped the paradigm. So for every positive case, for every positive test, we tell everybody how far away that positive test is, like a radar. Not just telling everybody who was adjacent that they were adjacent to a positive test. So on this one, I want to show an animation that explains what this would mean, because these are just words. What we made is we made an app where the app actually gives you a display that looks something like this. It looks like a weather radar, where the weather radar animates as, well, let's make it animate. The weather radar animates corresponding to the passage of time. And as the weather radar is animating, you can see the date is changing. If you zoom in, you can see, you'll see that the date's changing from June 4th, June 5th, June 6th, and so on. And as the date changes, we display how many positive cases there are. That's what the red bar is, how many positive cases there are. And the distance that the bar is to the right is indicating how many relationships away it is from you. What does that mean? So one relationship away means that you spend significant amount of time with that person. Maybe it's somebody you live with. 2 relationships away means that you spend significant amount of time with someone, and that person spends significant amount of time with someone else who you don't. Then that other person is 2 relationships away. So in other words, this could be something like your housemate's coworker. And 3 relationships away would just be maybe your housemate's coworker's kid. Now, our idea was, if you think about how COVID is spreading, the most relevant way to measure COVID's distance from you is actually not in feet, meters, miles, or kilometers, but in terms of how many relationships away it is. Because if you think about it, that's actually what the principle of contact tracing is anyway. You catch it from the relationships. Even if you live 5 miles away from your workplace, well, if somebody who sits next to you at work lives another 5 miles away, but is positive, that person is directly relevant to you. And the reason is because somehow you intersect at the workplace. Or if that person in their household has somebody else who's sick, even though that household is now maybe 10 miles away from you, that's extremely relevant to you because that's a distance of only 2 relationships away. And so our principle was you could make a radar. This is effectively as powerful as radar in warfare. And many people said at the beginning they thought that these kinds of apps were tracking people, and maybe people didn't want to install an app because their impression was this is an app that's tracking me. Indeed, if you now think about the incentives with the typical way that apps were made before and the paradigm that was used before, the way that the paradigm was before was that those were all apps that protected others from you. They were things to indeed track you, track other people, and if you suddenly became exposed, you would be asked to take actions that will protect others from you. With this different paradigm, once you build in the radar, once you build in the range and the lead time, that suddenly gives you the ability to have early warning. And once you have early warning, if you can see that COVID is now 7 relationships away from me, and then it's 6, and then 5, and then suddenly became 4, 3. At that point, this is showing you that COVID is approaching you directly, but out of your own self-interested behavior, you aren't asked to quarantine because it hasn't gotten to you yet. But in the interest of not getting sick, there are very, very many basic things that you might do, such as you might wear a mask, or you might wear a better mask, or if you have the option, you might choose to work from home that day. Or if you have to be in person, you might actually keep greater distance when you're interacting with anyone else at your workplace intentionally. Because this has finally become a way that could protect you directly from others. And I guess we mathematicians are always thinking about situations where if you flip the order of things, does the impact change? And so I guess we're always hunting for ways to flip things for which when you do that flip, you effectively change the sign and change the entire motivational dynamic. Actually, to jump forward a little bit to what happens with this kind of dynamic. I mean, with what we've actually made it into an app. I'm not just talking about something theoretical. And our app is in fact being used on a bunch of university campuses, such as Georgia Tech, Carnegie Mellon University, Grand Valley State University. And as we're being used in these different locations, we've actually even found that if we talk to people who are representing fraternities and sororities, these are great conversations in the sense that people see that the app, this particular approach, which empowers every individual person with more information so that they can just try to not get themselves sick if they want to, this is something that actually is quite palatable. And so jumping back to this chart again, I want to say a little bit about what's underneath and how this is computed. But the emphasis why I'm going back to this chart is that this technique could actually become the 21st century way to avoid infectious disease. Just like how satellites and radar imagery help to transform our protection or our prediction of hurricanes. Actually, if you look at the history of hurricanes in America or in other countries, it used to be that when the hurricanes came, people just died because you had no idea it was coming. And today we take for granted that you just, of course, have the satellite view or the radar, and you can see this huge cloud coming with enough time to take precaution. If I now take this and contrast it to the methods that were being used before our approach, the methods would effectively be like me just standing in front of this and blocking everything except for distance 1. Because they would only tell you if something got to distance 1. Distance 1 means your direct contact. Instead, what we do is we say, let's use the entire network. And does this tell you who it is? I mean, at distance 12, there could be thousands of people at distance 12. But that raw number of how many there are is actually what you need in order to see whether something's coming towards you. And to talk a little bit, some people are often wondering, how is this graph constructed? Well, the chart here is constructed by when you have the app installed as you're walking around outside, then the app automatically detects its relative distance from other apps, not the absolute distance. It does not track the GPS coordinates. That one actually would have major privacy implications. Instead, what it does is it uses a combination of Bluetooth signal strength and ultrasonic pings like sonar, in order to find out the distance between your phone and other people's phones. But it doesn't care whether your phone is in Pittsburgh or in Argentina or on the moon. And as you know, the moon has no GPS coordinates, because GPS coordinates are with respect to the surface of the Earth, and the moon's just like continually orbiting. But I'm emphasizing that our entire system is just based on relative distances. And now we declare that two nodes, two people, are connected in this network if they've spent at least 15 minutes within 10 meters of each other. Now you'll notice this is 10. 10 is pretty big. And when you think about contact tracing, everyone talks about 2 meters. But that's because when you think about the traditional way that people approach contact tracing, in the traditional approach, you are asking people to quarantine. And if you're asking people to quarantine, people want to make sure that, that they should be quarantined. And they don't want too many false positives. But with what we're doing, we're actually not directly asking anyone to quarantine. We're just helping people to have a radar that lets them know if they might want to be cautious. And if you think about it, wouldn't you want to know, or wouldn't it cause you to kind of be a bit more careful, and you'd want to be a bit more careful, if you had found out that there was somebody who works in the same general office area as you, who lives at home with somebody else, just lives in the same house as somebody else, and that person goes to school with, maybe that was their kid, maybe that person goes to school and is in the same classroom as somebody else who just tested positive. Actually, this is useful information, even at these 10-meter radii. And the reason why it's useful is because once you flip the incentives, flip the perspective, this is a behavior question, once you flip the perspective, in fact, the human tolerance to false positives and false negatives changes. When I say tolerance, I mean, what do we want, right? If you're being asked to quarantine, you generally don't want false positives because you wouldn't want to quarantine unnecessarily. But if you're being told whether or not there's potential danger, you actually don't want false negatives because you'd rather see more danger than less. Because at the end of the day, you're not going to necessarily stop everything you're doing. You might just simply know to wear a mask and keep a proper 3 meters away from people as you walk around. So this is actually the main point, is that somehow with this particular approach, we actually think that this is a fundamental improvement in how you might try to control the spread of any infectious disease like this one, any pandemic, in the sense that instead of letting the pandemic just spread around invisibly and occasionally asking people to quarantine in the hopes of stopping the disease, give every single person their personal radar. And if they have their personal radar, even though you now get to see if something is 3 away, do you know who that is? 3 away is now very far. But nevertheless, getting that signal that it's 3 away is what you need to put into your mind, just to put COVID into your mind and to see that maybe we should be careful. Let me say a little bit about, empirical outcomes, right? So far I've been talking entirely in theory. And so, as I mentioned, the system has actually been used, it was first released at Georgia Tech. And I'm quite careful, because we actually operate a real system that has people using it, we're very careful not to ever reveal any information that might only be accessible from our data sets, because we do want to maintain the confidentiality of everything. Even though we don't know any personal information, we still have a principle of not revealing any information that's inside the data sets. But fortunately, students like to post on Reddit. And so this is actually something that's just thrown onto the internet by a student at Georgia Tech. And the interesting thing is that they've said this comment that the charts are unbelievable. What charts? Well, this is a chart. So this is a chart. This is not the chart of how many positive cases there are, but this is just an example of how a system which aligns together with people's interests could actually potentially gain adoption. And not only that, its dynamic of gaining adoption could help more people understand that it's gaining like a snowball. And this is also because I'm saying these sorts of comments because my understanding is that this audience here has a lot of people who work in quantitative social science. And so if you're trying to think of what threshold is necessary in order for people to perceive that a critical mass has gone around the system, well, something that helps is if you can directly see that there are 1,000 people who are connected to you through this network that has all linked up. And in particular, this blue chart is not saying how many positive cases there are. This blue chart is just saying, for this particular individual, how many people were at distance 1 from that one relationship away? Well, that happens to be 2. There are 2 roommates who are 1 relationship away. And then after that is 3, meaning that those 2 people, among them, they were around 3 other people. And those 3 other people, by the way, weren't yet counted. So there are 3 people at distance 2 from this particular Reddit user. And then after that, there are 20 people who are not yet counted among the 2 or the 3 or the Reddit user, and quickly it just balloons into the hundreds. And the calculation, by the way, of what you need, for example, at a university campus to see something like this is actually minimal. In fact, if you think about it, if you want an app like this to go viral, like what was just demonstrated in that picture, you really just need that for every one of the users, they have at least 2 people that they're around who are on the system. And each of them needs at least 2 people they're around, and each of them needs at least 2 people they're around, and so on. Because that would cause an exponential explosion. And what you need for that, this is the probabilistic calculation, it's just that, you know, on average, how many people, what fraction of people need to have this installed. All you have to do is you just have to have have the expected number of connections of an individual inside the user network to be at least about 2. And well, it's technically at least about 3 if you want to have an exponential explosion. But if you want to have at least about 3, well, this is the user. There are n people that they typically spend time around. If p fraction of them have the app installed, about n times p. And if you need to have that n times p is around 3, on a university campus, how many people do you spend at least 15 minutes within 10 meters, 30 feet of? It's huge. And by the way, we collect our networks over a 14-day period. It's huge. So actually, we calculated that around 10% at a university, dormitory, or a school, like a K-12 school, that level of adoption would already give you that mountain that you saw there. Okay, so this is actually the main innovation of a different way of looking at the contact tracing. And I should also say, regarding the empirical stuff, this is just a long quote from a student newspaper that had been put. Actually, the student newspaper is from a university that's not Georgia Tech. It was a different university, University of Georgia, where the students were curious, what's going on here? And so again, I put this here because we don't disclose any statistics that could have been conceived of as being private information. But when I said this like 10% figure, that was actually what a spokesperson for Georgia Tech had actually said. Okay, right. So in a nutshell, what is this all about? This is a technique which we think could actually have an enormous impact on how you try to control the spread of a pandemic. And it's a real pleasure to have this opportunity to speak to this audience about this, because I come from mathematics. From mathematics, we think about the theory. We think about how to build something like this. I'll talk about the guts of it in a second. But after that, it actually does require many other experts, many other researchers working in all other fields to think about it, think about what we are proposing here. And if they see that there's value, we actually need your help. And I'm actually very serious about that. If there are any of you who are watching this who think that what was just described could actually be extraordinarily powerful in controlling not only COVID, but any future pandemic, now that we have smartphones and now that it's even possible, actually, we need your support. We need your support because this is representing a totally different paradigm than the paradigm of using technology only to accelerate the traditional technique. I put this thing here, this picture here, because this is a picture that illustrates the kind of breakthrough that this could be providing to everyone as they're trying to avoid a disease. Because this is an image of a hurricane. And we are all used to seeing this picture now, right? We're all used to seeing this picture. If you imagine what life was like 200 years ago when there was not this picture, people just died whenever they were on that coast. And what we're proposing is to give every single person in the world access to their own hurricane radar. And if you have this, even the small changes that it incentivizes in your behavior could actually possibly facilitate dynamic, focused, not quite lockdowns, but mini shutdowns in areas wherever the virus went. Because you see, if you are able to know that there's virus which is getting closer and closer to you, your level of paranoia, the increase in your level of paranoia, might just cause you to wear a mask. And there's now been increasing research about how if people are actively taking precautions to stop the spread of the virus, stop themselves from getting the virus, actually that also stops them from spreading it to others if they actually were sick. So, for example, if both of us, if there were two of us in a room, and if we both were wearing N95 masks, although the transmission probability is not zero, it's still possible that it can transmit, actually the transmission probability will have dropped by a significant amount. And if you're trying to control the spread of a disease, you don't actually need to completely stamp out the spread. You just need to make it so that that basic reproduction rate, that R0, drops below 1. And so what we are trying to do is we're trying to facilitate everyone to have this hurricane radar so that they would be able to all approach pandemics the same way that we today approach hurricanes. Now, I do want to say a few words about anonymity and about what is underneath the whole system, which is what makes this thing able to work. And anonymity is very important because actually what we've also learned when we're deploying our app in many places is people don't understand it. People actually assume, oh, well, if you're making an app that does this, of course you're tracking my GPS information, because how else would you find out who's been around who? That's where mathematically we emphasize the word relative. So the important thing here is we actually don't care where anyone is. That's not important for the purpose of this intervention. All we need for this intervention is the abstract network of which individuals spend time with which other individuals. And it doesn't matter where they are. They could be on the moon. Although, I guess on the moon you have enough personal protective equipment that you probably wouldn't infect anyone else. But in any case, if I was looking at this, right, what sort of methods do we use to measure the relative distance? Actually, we have some fun stuff underneath here, which is also representing technology that is not widely used. The first one is that we use ultrasound time, in the sense that when we're trying to find out the distance between two devices, we, in fact, will have one of the devices make an ultrasonic pulse, and the other device receives the ultrasonic pulse, and it measures how long it took for the ultrasonic pulse to go across. That's interesting. But I should emphasize that that's actually very precise. The way that we can do this with ultrasonic pulses is we, in fact, if you go and try the app, if you download the app, then you'll find out that the app even tells you how far away the other devices were that it was detecting. And that's an unusual step because, unfortunately, there is actually no other app that controls COVID anywhere else in the world that will tell how far away things are, because they only use Bluetooth. So the second one. The ultrasound in particular, though, is able to be more accurate because we're measuring the time that it takes sound to travel from one point to the other. If you compare to the other methods are using things like Bluetooth signal strength. Bluetooth signal strength, that's based on the principle that if a device is farther away, that the signal strength at the other device, if you have a Bluetooth transmitter here, signal strength at the other device will be weaker. And it follows a mathematical law, inverse square law, in a vacuum. So unfortunately, the techniques that are used for the Bluetooth signal strength don't perform as well when you're not in a vacuum, because there are other ways that the signal can be absorbed, or there are other ways that the signal can be amplified due to reflections off of, say, metal walls of a bus. And unfortunately, the Bluetooth strength method has never been shown by anyone to be able to detect whether you're within, say, 2 meters. Regardless, we actually use that too, because for what we do, once we change the paradigm and we change it away from just trying to identify if you have been around somebody else to tell you to quarantine, actually it turns out people would rather know that it was somewhere around, and they're willing to have greater error bars. And so that's the value of being more, of using the different paradigm. Along those lines, there's also the Wi-Fi access points. We also check Wi-Fi access point equality. We don't care which Wi-Fi access point you're on, but we just will check whether you are on the same Wi-Fi physical access point as somebody else for an extended period of time, several hours. And if you are, that's enough also to detect that you are a connection in the network. A fun fact about the precision, again, because I'm a little bit of a I guess, a scientific geek as well. This is a chart. I actually don't usually give talks that have charts in them because most of my talks are about mathematics, about theory. But what this is showing the experimental results of measuring the distance using our ultrasonic method, where the axis up here is what our device said that the distance was, and this axis here is what the actual distance was. And all of these different colored dots represent different kinds of scenarios. For example, the two phones might be obstructed by a certain very specific obstruction. And what you'll see is that there's a very consistent nature, that all of the reported distances that we have are bigger than the actual distances. And there's very little error in the other direction of our distance estimate being less than the actual distance. Why? Well, that's because of the laws of physics and the physics of ultrasound. The way we built our system was that we measure the time of flight of the ultrasonic pulse. Ultrasound cannot actually penetrate through every object, so sometimes it reflects around. Reflects around in the sense that it could reflect off of my chin, off of your chin, and then down to your phone. But the reflected distance is always at least the actual distance, because the shortest path between 2 points is the straight line. And why this is important is because we actually use the ultrasonic part to, you see, we actually also do some things that help to facilitate the first paradigm, the original paradigm. We also do believe that it does make sense to tell people if they've been exposed. But for our system, we'll only tell you you're exposed if we measure your distance, and our estimate of your distance is that you were really close to the other person. And due to the inequality here, where our estimate is always an overestimate, if we think that you were close, you definitely were close. That's the value in having one-sided error where everything is always above the line. So I thought I'd mention that. This is just like, I guess that's a fun engineering, mathematics, and science angle as well. Now, I had mentioned that the Bluetooth has issues. This, if you're curious at all, this particular reference indicates that, unfortunately, when you use Bluetooth, there are major issues of the distance measurement just being way off. In fact, this particular set of researchers found out that they observed that the received signal strength need not decrease with increasing distance. So in some situations, you'd go farther away, and the signal strength actually got bigger. Anyway, we don't use the Bluetooth for that precision level, but we just use it to generally construct the network. One other piece maybe I should mention that is not completely trivial about what we've had to do is that, well, if you want to actually implement this, you have to write algorithms that could compute on a very large graph, because we do want to make this thing usable by a large number of people. For that, it's helpful to have connections with Carnegie Mellon University, where there's some very talented people from the alumni and the student background. And I personally also used to do quite a few things in algorithms for the purpose of graph theory algorithms. And I'll just say that the heart of the innovation for how we're actually able to calculate on a huge N is based on using approximation algorithms instead of computing things precisely. Because unfortunately, if you wanted to be able to analyze things precisely, you'd be running into what are called quadratic time algorithms. And if N is a billion, your quadratic time algorithm will time out. But by cleverly deciding what things to approximate instead of computing exactly, we're actually able to compute things efficiently, even for huge scales. We currently don't compute it with N to be a billion. Right now, our N is probably something around 100,000. Now, I also want to emphasize one last piece here, though, which is that there is a huge benefit to trying to do things with this approach that I'm talking about, because it also lays the foundation of an ongoing response to a fluid situation. Because now that I've talked about this alternative paradigm, really the alternative paradigm also has another huge benefit, which is that it actually gives you this network, which has no personally identifiable information linked, but that network lets you see how COVID actually spreads. And if you know how COVID actually spreads, that might give us a way to be able to control the disease more effectively, especially after we start having different kinds of vaccines that are starting to go out into the public. What should be the response if they took vaccine candidate A? I shouldn't call it candidate. They should be actually released, right? What should you do if somebody has taken vaccine A and then they're exposed to this particular strain of the virus which is coming along? Is vaccine A effective or not? These are all deep questions for which there's no way to get a solid answer unless you are actually doing something like what we're doing here. All right. So that brings me to wrap up. What we've made here is we've presented a new and complementary paradigm. Complementary is an important detail. You can do both paradigms at the same time. They're not in conflict with each other at all. But the idea is very simple. For every positive test, just tell everyone how far away it is. That's it. But somehow, what that gives everyone is headlights to drive in the dark. I was talking about radar before. Another analogy that makes sense is if you're driving at night and if it's pitch dark and if there are no street lights and you're outdoors, out in the countryside, of course you'll turn on your headlights. Why will you turn on your headlights? Because it protects you against running into trees or against running into other cars. Nobody ever objects about turning on headlights in pitch darkness because it's useful. And furthermore, because of headlights, we can drive at night. You can drive at 65 at night. Maybe some of you drive faster. You can drive at 70. But because you can see what's out there, you can actually drive around. And so what we're trying to do now is we're trying to help illuminate this idea to the world. If you are interested in this at all, if you come at this from the behavioral science perspective or the quantitative social science perspective, if you see that this particular angle might actually be quite interesting from your research perspective, or if you think that this actually could be a powerful intervention that could help us all stop the spread of COVID, I'd love to chat with you. Feel free to contact me afterwards if you'd like. You can find me. I assume that my name has been sent out with the rest of this talk, but if you just go to Novid, which is the website of the app that we've made to make all of this possible, you'll be able to contact Novid. And if you contact Novid, I'll be able to see it. So thank you to everyone for your time. And I'm happy to open up to answer a few questions if people want to ask anything interactively here at the end.
Thank you so much, Dr. Lowe, for your presentation. That was great. So right now we're going to open up to any questions. Tom, I see you've already unmuted yourself. You can go ahead and you can also unmute yourself as you want to ask questions, or you can also send a note in the chat. Okay. Thanks, Tom. Go ahead.
Yep. Well, first, thanks for the great talk, Dr. Lowe. This is really interesting. So I think one of the things that we've kind of seen with this whole situation is that people aren't very good about reasoning about complex systems. And kind of this radar is kind of telling us a network distance that the disease is away from us. So given that people are probably not familiar with, sure they understand like what two relationships away means, but they might not be able to reason about how much of a risk that actually is for them. So has that been kind of a consideration in how the app is kind of built to tell people how the risk is, and like what kind of went into that process, if so?
Yes, thank you very much for asking that question. Actually, the idea for the app might have been mathematical, but the execution of it was done with human-computer interaction folks and designers to think about how we can communicate this to the general public in as easy a way to understand as possible. And in fact, I should say, when I came up with this whole idea, the first two people I brought on the team were user experience designers, both from the Carnegie Mellon University community. Now, you'll notice the way that this was laid out is a way where, I'm not sure if you can see on your screen, but it says close up here. So there's you, and there's close, and then there's all this stuff going out to 12. The reason it goes out to distance 12 is because we actually want you to be careful as soon as it gets to distance about 3. So this is sort of like driving. The way it's been designed is that if the disease is coming towards you, by the time it gets to 3, it looks like there's red filling up the screen. And generally speaking, a screen full of red seems to cause people to have some level of concern that something is coming close. That was intentional, and that's why it goes out to 12. Because if we want you to be concerned at 3, we want that to already be the majority of the screen. I should emphasize why 3. 3 is relevant for a certain reason. It's because we want you to be concerned at a time when there's still time to protect yourself. And due to the lag of time before when somebody actually has a positive test and confirms positive, right? What I mean is that you first have to already be positive, then you have to be a few days after positive, then you have to take a test, then you have to get the test results. By then, actually, COVID might be distance 2 from you, if that makes sense. That's why 3 is drawn here. But if you look at the way this has been designed, It's like driving now, right? The way to deal with this is you don't even need to know network theory. Your whole game is just don't let red get all the way to you. And this is the danger zone here already marked. If you see red getting in here, you should get scared. Because, by the way, you know what it means if you get hit with red? It means that you tested positive. So we actually went for this method as opposed to what many people were trying to do. Other people were trying to do things like assigning a score, of saying that your score, your COVID risk score is 425. But what does that mean? It's very hard for people to understand what that means. It's a lot easier to say, it's like driving. If I'm driving and I see the median of the highway, the big concrete thing coming up on my left, I steer away because I don't want to smash into the median. So the way this is you're driving effectively. If you see COVID coming closer to you and you don't like it coming that close to you, you put on a mask. You decide to be a bit more socially distant. And what that will do is that will make it harder for COVID to get to you. And of course, what we are hoping is that you also, actually not just what we're hoping, we know that if you see something, you will tell other people, even if they aren't using the app. That's actually one of the powerful things here. It's because with the normal methods that people were using, the existing post-exposure notifications, it wouldn't be as easy for someone to tell someone else, hey, I've already been exposed. That's somehow, that there's a stigma. You've already been exposed. But it's a different story to say, hey, I see that something is coming. It's like you're bringing bad news, but it's not your fault that you're bringing the bad news. You're just giving everyone a heads up that something's coming. And if you cause your radius 1, 2, 3 circle to become more cautious, that's actually going to directly protect you. So I'm not sure if this helps to answer your question, but we tried to design this whole thing so that it would be as easy to interpret as driving and try not to crash into something.
Yeah, that's a great answer. Thanks.
Yeah, we didn't even try to draw the graph. We didn't try to draw the network. That's too deep. Are there other questions?
So, hi, this is Eli. So great talk, by the way. And my question to you is how dynamic is that network? So are you working like with a static network, or is it constantly like being adapted?
Yes. So what's happening right now is every single hour we recompute the global network. And this is why the algorithms are important, because we need to be able to do this efficiently. And so what happens is every hour when we recompute the network, what we do is we say, okay, we're going to snapshot as this is the end, this is the timestamp of the network that I'm generating. To construct that network, we look back exactly 14 days, specifically 14 times 24 hours. Now, when we actually back to you is the other way. Sorry. So back is this way, right? So if this is the snapshot of the end time, we go back by 14 times 24 hours. Now we've got a long period during which we check every single interaction that happened between anyone who's using the system. Based on this, we construct the entire network of who typically spends time around who. Notice this is not the same as the network of how you're going to transmit the virus in the future. This is simply, all we're trying to do is we're trying to figure out what is the backbone of the network that underlies society. And that's why all of our systems are calibrated to be pretty generous. Now, once we calculate the backbone, this is designed so that it would capture, if you live with somebody else, yes, that would be captured. If you work with somebody else in the same office, captured. If you typically hang out with somebody, also captured. And because those are all captured, then we finally say, okay, are there any new positive reports? If there are any new positive reports, we say, oh, looks like there's a new positive report. Let's go tell everyone how far away that positive report is from them in their network as of this snapshot. Importantly, if that positive report continues to wander around in society afterwards and sit in the middle of lots of people, we will actually say nothing, because that would be a privacy consideration. And also, we're not trying to make a house arrest app. If you want a house arrest app, someone else can make that. We assume that if the person actually knows that they're positive, they've been given some suggestions to do certain behaviors. And if somebody wants an app to enforce those behaviors, use a different app. But what we do is we provide a way for them at that point to notify all of the rest of the network of their innocent pre-knowledge of being positive behavior, in the sense that if there are people that they typically spend time with, those people would find out that something's at distance 1. And if there are people that they typically spend time with who spend time with someone else, the other person sees distance too. And then we just do this every hour. Did that help to explain the system?
Yes, it did, actually. And this brings me back to a second question, is that in terms of privacy now, not in network science context, if a crime happens, can law enforcement track activity through your app? Have you thought about things of that sort? Or
Yes.
like if it can be used, or if it has the right to be used for other things like that, for example, or kidnapping or whatever that is?
Yes. So actually, I want to emphasize that all the things I've talked about today, there's in fact an article that I've written. I've put it on the archive. It went on the archive last week. It's in math.cy, Computers and Society. And it's about 20 pages. It details all of these aspects that I've talked about. And it also has it has a section on privacy. To answer your question specifically, the value of this to law enforcement would not be at that high because there's no absolute location, only relative. But even then, if there's only relative location, I should also emphasize, this app is not run by a government. We run it. But by the way, the same thing is when I say we run it, if the government wants to know if people have been around other people, if you just go and ask Google, Apple, or Facebook, they have location services which are actually always running, which are not necessarily using your GPS, but using other things. So if the government wants to go to a non-governmental entity to find this information, such entities already exist. We're not inventing anything new. On the other hand, if the question is what could you deduce if you were not, suppose you were the government and you did not have privileged access to the data, you actually would still have difficulty trying to come up with what you just described, in the sense that you might be able to find out if two people were generally around each other at some point in the last 14 days. I detail inside the paper, I detail a certain way you could deploy some agents to be around some people, have the agents fictitiously report positive, and then you'd be able to see something that happened. But the only information you'd get from that is that somehow these two people in the last 14 days had been within 10 meters of each other somehow. And you wouldn't know when. But I wanted to be a full disclosure, so that somehow this whole thing is detailed in precise details because we don't want to create something for which it's that, afterwards people say, well, you could do this, this, and this. I should also emphasize, even though I said you could do it, it's not actually completely trivial to do it.
Thank you. That answers my question. And I guess I'm sorry for asking too many questions. One last
no.
So it's very interesting. I'm very interested in that, and my background is network science, and I like that stuff a lot. So I guess from here going, what is the next step for you guys, for you and your team? So what is the next thing to do? If just like marketing right now, just marketing the app, or is there any more like fundamental research to be done?
Oh, the fundamental research is already done. The app is already built. In fact, the biggest thing that we need now is for other scientists like you who look into this space and independently draw a conclusion that there's something going on here which is transformational. It's a transformational innovation. It's not just some incremental thing. This thing could fundamentally shape how we fight COVID. Actually, what we need now is that the scientific community has independent thinkers who are willing to go and speak up about this. Because right now, I'm the only one making a voice about this. And unfortunately, I'm fighting against groups which have lots and lots of money, which maybe aren't interested in solving the problem, but are maybe more interested in selling some app that does the other thing, the other method, which, as you saw from the way I brought up some statistics earlier, those other methods might be fundamentally flawed in the sense that if you aren't sure, if the chance of being positive when you're told to quarantine is relatively low, will people actually follow? Those could be dead on arrival, all of those apps. And so effectively what's going on now is we're trying to gain the support of people like yourself, people like the ones on this call, who think about behavioral science, who think about quantitative social science, who can actually help to raise the voice that there's something that's very unique that has just happened here. And furthermore, that it should be put into action now. You see, we've actually made it. It's already been deployed. And all we need is that areas like cities or schools or universities decide to join. And the reason why they aren't all joining right away is because it's different. And whenever there's something different, people say, well, I don't know. You've got one mathematician who thinks it's good, but does anyone else agree? And that's what we need the most.
I see. Thank you so much. So I guess if I want to take the app for a test drive, is it free, public, or is it what am I supposed to do? Is it free of charge? Is it just easy download? Awesome.
You just go to the Apple or whatever phone you use, search for Novid, COVID with an N, Novid, right? Search for Novid, download the app, and it works. And if you download it on a whole bunch of phones, for the testing purposes, you can go ahead and self-report some positives, because those are just you testing it with yourself. Whenever we actually deploy it in a city or in a university, we turn off the self-reporting, and we have authenticated reporting that happens through another server where we work with the city. Or we work with the school. So yes, please do. And actually, if you find this interesting, and if you would like to add your voice to actually stopping the spread of COVID, please feel free to reach out.
Thank you so much, Dr. Lowe. I'm going to stop everything there because I know many people are going to want to jump off because it's 5 o'clock. Thank you so much for presenting to our group. Everyone, Dr. Lowe mentioned an article in the circulation in the notice about the talk. There was a hyperlink for his article. If anyone else is interested and didn't get the link, feel free to reach out to me. I'll be happy to forward. I just wanted to let you know our next seminar is on the 27th. Zirak Wasim will be joining us from the University of Sheffield. He is a computational social scientist, and we'll also be talking about some relevant current events. So I look forward to seeing everybody then. But thank you again, Dr. Lowe, and take care.
Great. Thank you. Take care, everybody. Bye-bye.